Okay, we're going to talk about topics in Chapter 3. To begin with, we're going to discuss functions. Let's say we have a relationship. So say we have this group, Bob, Tim, Ben, and Sue. And we relate them to the color of shoes they're wearing. So we might have, let's get some colors going here. Bob, say, is wearing red shoes. Tim is wearing black. Ben is wearing brown. And Sue is also wearing black. So we have this relationship between what we could think of as input ideas. So if we input Bob, it outputs red as his shoe color. If we input Ben, it outputs brown, so on and so forth. Notice that Tim and Sue both output black. Well, we can say this is displaying functional behavior. That is, a function is a relationship, like this Bob, Tim, Ben, and Sue, that assigns a single element from the input, for example, say Tim, to a single element from the output. Tim is assigned to just one element from the output, and that is black. Sue is assigned one output, and it's also black. Bob is assigned one output, that's red. This is functional behavior. This is a function. On the other hand, say we have a relation, Bob, Ben, Tim, and Sue, and we assign colors of scarves they are wearing. Bob's wearing green, Ben's wearing orange, Tim's wearing red. So far so good. This is functional. Each one of them has only one, but Sue, always the fashion specialist, she's wearing a green scarf and an orange scarf. So she has two for her input as Sue. The input of Sue has two outputs. This is not functional. Not a function. Well, this idea carries over into equations that we use, and we'll often denote these equations as functions or not functions. But suppose we have a relationship that looks something like this. I don't know, just a line that's a squiggle. Then since we look at this thing, and for a particular x value, we have a particular and only one y value. So for any x value we pick, there is only one y value. Sometimes it's the same. Sometimes, if we pick an x value, our y value might be negative, but again, it's only one and only one y value. We say that this plot demonstrates y as a function of x. On the other hand, suppose I have a plot of a relationship that looks like an egg here, or a circle, or an ellipse ellipse actually. In this problem, you can see here that for some particular x1, I have a particular y1 over here, and for this x0, say, I have the same y1, so that's okay, that's functional so far. But if you'll see for both of these, for this x1, I have also y1 down here, so I have two different values of y. And the same deal for x0, two different values of y. And they're actually pretty close to the same value. That's just a coincidence. We could have x2 over here, and you'll see that we'll have a y2 here and a y2 up here. So for one x value, so in this case, y is not a function of x. So function over here, not a function here. Now one quick way to determine this is what we call the vertical line test. Suppose you take a vertical line, and if you only cross the x-axis once and the plot once, then it's a function. On the other hand, if you look over here, vertical line test, I cross the x-axis once, but I cross the y-axis twice, so it's not a function. So the vertical line test. Vertical line test is a good way, if you have a plot, to determine if that plot is exhibiting functional behavior. Now when we're talking equations, we often represent equations. Say we have this equation y equals x squared plus 3x plus 8. Well, as it turns out, this is a function. F of x is how we would represent it, or we could say this is the same thing as f of x, or y is a function of x. Here's a graph of that function in this plot. This is the y-axis. This is the x-axis. You can see that if I do a vertical line test, that if I cross the x-axis, or for any point on the x-axis, I only cross the graph once. You could put in any number of vertical lines here you want. So this, in fact, yes, definitely is a function. One way we can figure that out is by creating a table of inputs and outputs. So when x is 0, y is 0 plus 3 times 0 is 0 plus 8 equals 8. When x is 1, for example, y is 1 plus 3 times 1 plus 8, which is 11 and 12. Let's do negative 1. When x is negative 1, y is 1 plus 3 times minus 1 plus 8, or 8 minus 3 is 5, plus 1 is 6, so on and so forth. And you can see here that this is the point minus 1, 6, the point 3, 8, 1, 2, 3, or the point 1, 8 is here, or 1, 12 is here. This is the point 0, 8, so on and so forth. We can plot these points and see that there's only one x value per y value. On the other hand, if we have x equals y squared, then let's set our table up again. For a particular value of x, if I have x equals 0, y equals 0, that's the first point. If x equals 1, y equals 1, 1. Here's another point. If y equals 2 squared, x equals 4. And we can continue on here. So far so good. This looks good. But this is what we call the principal root. There's a problem here because this is the same thing as 1 times 1. This is 2 times 2. But also, minus 1 times minus 1 equals 1. And minus 2 times minus 2 equals 4. So we actually have points down here too. Minus 1, minus 2. So the full plot of this, outside of the principal roots, is something that looks like this. It's a parabola that opens up to the right. And if we take and try our vertical line test, you will see that for any particular x value, we have 1 2y value. So here, y is not a function of x. Even though it's a valid equation, y is not a function of x. Whereas up here, y was a function of x. Similar plots, but this is a parabola opening directly upwards, and this is a parabola that opens to